Good morning, my name is Marco Cremaschi from the University of Milano Bicocca, and today I will present MantisSE, an enhanced and efficient approach to a complete semantic table interpretation. This approach was defined with the collaboration of Roberto Vogadro, Andrea Barazzetti, and David Chieregato in the Department of Computer Science, Systems and Communication of University of Milano Bicocca. MantisSE is the newest version of MantisTable. The underlying approach is comprehensively improved over every aspect of semantic table interpretation tasks. Besides to MantisSE, we also developed a utility tool called LAM-API that allows to efficiently search into Wikidata or DBpedia in order to sharply reduce computation times required by querying an online RDF endpoint. LAM-API is an API specification which allows to match labels with full text search capability and fuzzy matching. For performance, our LAM-API implementation uses an Elasticsearch instance for DBpedia and Wikidata. In order to retrieve useful data for every STI phase, LAM-API also allows to return information about literal values, object values, concepts for an entity, and predicates given to entities. LAM-API offers a great flexibility to choose which knowledge graph should be used for annotation and allows to seamlessly add any knowledge graph besides DBpedia and Wikidata, since the methodology is completely unsupervised. The non-destructive approach implies that all results are sorted and scored but never removed until the export phase, where user is able to apply a threshold to annotation and cut out the worst results. Results revision is possible because of the non-destructive approach. For example, CEA results are enriched with the result of the next phases like CPA and CTA. Performance has been vastly improved by a factor of 12 compared to the previous version, and accuracy has been greatly improved in all STI tasks. This slide shows the 8th step of MantisSE approach: data preparation and normalization, column analysis and subject detection, data retrieval, cell entity annotation, column predicate annotation, column type annotation, revision, and export. The first phase prepares the dataset and normalizes the strings from the input dataset. We then proceed to analyze column to annotate name entities and literal column, and we detect the subject column, which both are very important for our methods. The third phase retrieves data from our knowledge graph endpoint. This phase is where LAM-API is mostly queried for the entity label using fuzzy matching. The next phase, cell entity annotation, is the most important since all other steps depend on this. We then proceed to annotate predicates and concept. Revision is our last computation phase, where all previous results are put together and rescored. Export phase allows extracting winning annotation based on some criteria. Without loss of generality, let's see what's happened when we insert the following table in our tool. First step is to clean the data. Notice how all the strings are now lowercase and mixed punctuation. Warner Bros. With capital letters and the dot at the end become all lowercase. Literals too are normalized in a single format, like for example the worldwide gross. Dates are tricky because in this phase we are not able to judge if 2015 is a year or a number, but in general we can normalize them too in a year, month, day format. Next, we analyze columns and assert if they contain name entities or literals. We also seek for the subject name entity column using the formula in this slide. In this formula we use different features, for example, fraction of empty cell, fraction of cell with the unique content, distance from the first name entity column, and average number of words in each cell. Retrieving data implies to seek for the entities in the knowledge graph with similar labels to our name entity cells. For example, if we query Jurassic World on LAM-API Wikidata, we get a list of candidates: Jurassic World with type movie, Jurassic World with type comic strip, and Jurassic World with type attraction. Regarding the data retrieval phase, this slide shows example of labels imported into LEM API. These labels were extracted from Wikidata and DBpedia respectively. Thanks to LEM API, we can obtain, given a string, the list of concepts, predicate, literals, and objects associated with that string. In the fourth phase, cell entity annotation, the main problem is the discrimination between candidate entities, because there are many different entities with the same label. We annotate by row by computing the following confidence score. For the name entity cell, the confidence score is equal to 1 minus edit distance. For the literal cell, we compute different confidence scores for numeric, string, dates, data type. In the end, we obtain confidence score for the row by average confidence of cells. For all confidence scores, the range is between 0 and 1. Ideal high confidence subject candidates have a zero edit distance between table cell and knowledge graph and are fully linked with other cell candidates with zero edit distance. In this phase, we don't apply any threshold to seek for winning annotation. With all cell entity annotation candidates with row confidence, we simply assert that the highest scoring predicate is the most frequent. Therefore, we apply the following procedure. Compute predicates relative frequency, apply divide by maximum normalization of relative frequencies. In the example table, predicates are extracted from column context of the previous row annotation candidate. For example, from Jurassic World entity and Colin Trevorrow, the approach extracts Wikidirector property. In the column type annotation, we retrieve the concept corresponding to every candidate entity from LEM API. For every column, we use an in-memory structure storing frequencies of the common concepts as shown in figure in this slide. The frequencies are stored with by-max normalization in order to be homogeneous. For every column, the winning concept is chosen as follows. Concepts with the frequency lower than 0.95 are discarded in order to reduce the needed computation on the fully connected Wikidata concept graph. Columns are taken as every possible combination of couples for every single table. The final concept selected is the one with the highest number of connections in the graph matching the column of the table. In the revision step, entity linking results are revisioned with the column contents of CPA and CTA. Since all phases scores are in the range of 0 and 1, we are able to revision CA result by multiplying confidence. Ideal case where there are no ambiguities will produce a confidence of 1. In this phase, we don't apply any threshold to seek for winning annotation. In the final phase, we seek for winning annotation. Therefore, we apply the following procedure. A custom threshold is applied to cut out low confidence annotation. Maximal confidence annotation are extracted from revision results. In the following slides, we will show a complete example with an explanation of the inputs and the outputs of each phase. In the following slides, we will describe the web app that allows the use of the MantisSE approach through a graphical interface. In this web app, the user will be able to upload a table or a dataset and choose one or more LAM API endpoint to be used for processing. For example, LAM API Wikidata or LAM API DBpedia. The process will be executed in the background, but the user can be able to explore results when finished. Therefore, as just said, once the processing is complete, the user can explore the results for each main phase: CTA, CPA, and CEA. CPA and CEA steps will be displayed in table form, while CPA in a graph form. In this screen, we have the result of CTA step. Below each column header, the annotation with the highest score is displayed. A similar view is shared with the CEA result, where results are displayed below each cell of name entity columns. Also, the UI shows in the top area which endpoint has been used and provides a way to download the annotation. As previously seen, the approach is non-destructive, and each iteration is saved so the user can be able to examine the whole process further just clicking the icon beside the chosen annotation. In the Annotation Detail view, the sidebar will be open to display all the annotation retrieved for the selection with the respective score grouped by the endpoint. In future, we'll provide a way to edit the final annotation choosing from the displayed list. This view will be available for each phase. To better display the CPA annotation, in place of a table, a graph has been used. Each node represents a column with the corresponding annotation, while each arc is the relationship between two nodes. Regarding final remarks and future plan, we underline that the CEI does take in consideration only directly linked entities. This is likely the most important source of missing wrong annotation. This is going to be solved in the next version. CPA is directly computed from CEI results, but some ambiguities still remain. A slightly more complex algorithm is currently under development. CTA will possibly be extended by using space representation and feature-based similarity score, for example, embeddings. Thank you for the attention.